In this video, we will discuss Hall effect in detail. Ever thought of how electronic speedometers work? And how does the anti-braking system work? This is because of the Hall effect. There are numerous applications for Hall effect, such as proximity sensors, electric treadmills, 3D printers, automotive fuel level indicators, positioning sensors, etc. First, let's see what the Hall effect is. The production of a potential difference across an electrical conductor when a magnetic field is applied in a direction perpendicular to that of the flow of current. Let us take a conductor connected to a battery. The electrons inside the conductor take a straight path. Nothing is unusual about it. Measure the voltage across the conductor. It shows 0. Now, what Hall discovered is that if a perpendicular magnetic field is passed through the conductor, it behaves differently. Now, arrange two magnets perpendicular to the conductor so that the magnetic field passes from north to south. What Hall measured is that the path of the electrons through the conductor starts to curve. Electrons get pulled to one side of the conductor. This is because whenever the electric charge is moving through a magnetic field, the electric charge will feel a force. We know that the moving charge creates a magnetic field. This magnetic field interacts with the external magnetic field and induces a force in one direction. This force is called the Lorentz force. The direction of the force is given by Fleming's left-hand rule. So, the electrons start stacking up in the direction of force. As a result, on the other side, there is a scarcity of charge carriers, so we assume equal and opposite charges here. So, this makes one end of the conductor to be negative and the other end to be positive. This is what we call potential difference, in other words, Hall voltage. This separation of charges creates an electric field from positive to negative. As a result of this electric field, an electric force will act on the electric charge. The electrons keep stacking up here until the electric force on charge becomes equal and opposite to the magnetic force. In other words, after fully stacking up, the next electron comes and is attracted towards the positive side, and at the same time, there is a magnetic force that wants to sweep it to the negative side. So, the balance of these two forces makes the electron go straight, as if there are no forces. It acts like there is no effect at all. This is what we call the Hall effect. In this steady state, if we measure the Hall voltage and the current passing through it and divide them, we get Hall resistance. Now, let's examine the Hall effect situation when the magnetic force and the electric forces are equal. Magnetic force is equal to the quantity of charge multiplied by the velocity of electron and multiplied by the magnetic field exists in this region. And electric force is equal to the quantity of charge multiplied by Hall electric force. By equating both, we get this equation. And we know that V is equal to ED, where D is the width of the conductor. By substituting EH value in this equation, we will get Hall voltage, VH, as follows. If it is a semiconductor, we can determine the concentration of the charge carriers or the magnetic field. The Hall voltage is given by the expression where P is the concentration of charge carriers, T is the thickness of the semiconductor, E is the charge of an electron. Then the Hall coefficient, RH, is given by. The main purpose of this whole Hall effect thing is, if you place a current-carrying conductor in the magnetic field, we can measure that magnetic field using the Hall voltage. Let's see how the Hall effect is used in speedometers. Well, small magnets are attached to the car's rotating drive shaft. And a Hall effect sensor, we call it a conductor, is positioned nearby to the drive shaft, leaving a very small gap between them. While the shaft is rotating, each time the magnets pass the sensors, they generate a small brief pulse of Hall voltage. When the magnets are away from the sensor, there will be no voltage. So every time it passes by, the sensor cuts the magnetic field and generates a pulse. and the counter increases. Each turn indicates 1 revolution. This is how revolutions per minute, RPM, is calculated. An electronic circuit counts how quickly the pulses arrive and converts this into a speed displayed electronically on an LCD display. Since the circuit is measuring the number of wheel rotations, it can also keep account of how far you've traveled. It actually calculates the static magnetic field using Hall voltage. When the magnets are away from the sensor, the magnetic field is recorded as 0. And when the magnet passes by the sensor, it calculates the magnetic field. This sensor phenomenon is used in numerous applications in cars. This calculation of the static magnetic field is a clever bit of science discovered in 1879 by American physicist Edwin H. Hall while working on his PhD. This is just 6 years after Maxwell figured out electromagnetism. Hall's work was ingenious and years ahead of its time, even 20 years before the discovery of the electron. In this video, we have discussed the Hall effect.